I'm just going to go through this variable linear voltage power supply. I'm just going to show you the circuit that is used to build this and how it works. I'm going to go through each of these sections one by one. So we're going to talk about this section here, which is these two coils of wire. That's called the transformer. When that signal goes through these components, it's termed as rectified. We're going to explain what rectification is. When this rectified signal is at this point here, this capacitor smooths it out. And I'll explain how this capacitor smooths it out in another section. And then finally, the last section we're going to talk about is the regulation. And basically it takes that smoothed signal and it makes it even smoother, if you like, and makes it a fixed DC voltage. So we're going to explain about each one of these units. So we'll talk about the transformer section first. So what is a transformer? Well, basically a transformer is just two coils of wire next to each other. I'll show you a typical transformer. Here's a transformer. This is what they look like when you buy them. Now inside there you've got a big iron central core which is not connected to anything, and then wrapped around that iron core are two windings. One winding is known as the primary winding, which I've represented here. This is the iron core in the middle, and the other winding is known as the secondary winding. As you can see in this diagram, they're actually physically not connected in any way. So what we've got here is a transfer of power between this primary circuit and this secondary circuit, and I'll explain how it does that. Now at the mains we've got an alternating voltage. You've probably heard of 240 volts AC. That means 240 volts alternating current. So what's happening is, from this 240 volts mains that you plug into your mains, you're going to have through the brown wire, the charges are going to flow in this direction, and they're going to go all the way through this coil, back out, and then back into the blue wire, back to the local substation that might be up the street somewhere. So in the substation we're getting our power basically. At 1/50 of the second the charges are all flowing in this direction, and then in the other 50th of a second the charges are all going to be flowing in the other direction. That's because at one moment we've got a high potential on this side and a low potential on this side, and at the other moment, at 50th of a second later, we've got a high potential on this side and a low potential on this side. Now, as you know, if you have a high potential and a low potential, then charges are going to flow from the high potential in a completed circuit down through into the low potential. Now, because we've got a completed circuit here, you can see that the charges are going to flow. They're going to flow, and they're going to flow that way, that way, that way. 50 times a second. It's going to be continually doing that. What's interesting about this, when you have two coils of wire next to each other like this, and you actually send a current through one coil of wire, it causes charges to flow in the nearby secondary coil of wire. Now this is done by a process called induction. I'm not going to go through all the details of induction, but all you need to know to understand how this whole circuit works is that for whatever reason, when you send charges through a coil of wire, it generates a magnetic field around that wire, and that magnetic field also impinges on the second wire, and it's just a fact of nature that if you have a magnetic field wrapped around a coil of wire and that wire is actually a completed circuit, you'll actually drive charges. It actually forces charges to move through that circuit. That's quite amazing, and that's what happens. Because of this, we're able to convert our 240 volts to a lower voltage, because the other thing that's useful with these two coils of wire, if the second coil of wire is much less windings than the first, you get a reduction in voltage, and that's what we want. With a transformer, what we're trying to do is reduce the 240 down to a manageable level, something like 12 volts in our case, or in the guitar amp it's about 24 volts. So what we've got here is 240 volts being converted via the action of this transformer, which I've just described, down to a voltage level of about 24 volts. So that's what it does. And then because we've got this completed circuit here, in this case I've used a resistor here, but if you measure the voltage drop across that resistor, so if you've got 240 on this side and you've arranged the turns on the secondary so that you'll get 24, say you have a switch there and you complete that circuit, you're going to measure 24 volts across there. So this is how you can transform a high voltage to a low voltage, a safer voltage if you like, because a lower voltage means that you can only pull out a small amount of current due to Ohm's law, V equals I times R. So if you have a high current, that can be dangerous, but if you convert 240 down to 12 volts, 12 volts is never going to hurt you in any way. There's no way it's going to be able to produce enough current to hurt you. Let me just show you the result of that. So remember, we've got this 240 volt AC signal. So this is coming in 240 from peak to trough here. Now when we go through the transformer, we've got exactly the same shape. The only difference here is it's reduced. So you can see here that these peaks are reduced compared to this one. So that's all the transformer does. So let's go on to the rectifier and talk about that. Here we've got the rectifying stage. So what does that mean? Well, we've just drawn the transformer down here again, just fitted it in. We haven't shown the AC supply here, just showing the primary and the secondary winding. Now, as I said before, the charges are going in this direction and they're swapping over and they're going in the other direction. That's happening 1/50th of a second. Remember, it's 50 cycles a second for UK mains. So every 1/50th of a second, these charges are going to change direction. So as we know, when it comes through onto the secondary, we're going to have the same effect. So here I've just represented one of those directions. Let's just look at this as being plus, and this is being the lower potential. So this is the highest potential, which we're going to call plus, and this is the lower potential. Now the reason we got a plus down here is because the action of the induction via the magnetic field from the primary has actually forced charges to move in this direction for that period. Therefore, when charges are moving through this coil in this direction, very much like a battery. In a battery, if we had the minus potential, we would use chemical energy to push those charges up to their higher potential. Now, with a secondary winding in a transformer, it's not chemical energy we're using, it's this magnetic field that's causing these charges to actually move through induction through here. So the magnetic field is pushing these charges in this direction. Now, because the charges are being pushed in this direction, wherever they leave, we can designate as the plus terminal, because that's the higher potential. The same with a battery. We call the plus side of a battery plus because charges, the conventional view of charges, they leave that terminal. So in this case, we're saying that the charges are moving through the secondary wire in this direction. They're going down here. Therefore, this side we're going to designate as the plus potential. So that means charges are coming out, they're moving around. Now they get to this point here, what are they going to do? Well, they can't go through this diode. This is a series of 4 diodes. They can't go through this one. Charge can only flow one way through a diode, and that is given in the symbol here as the bar. So if a charge is going up against a bar, it can't go through, so they have to go through this way. Now the charges will go through this way and they get to this point here. Again, they can't go through that diode, so they go through here. We've got this resistor here representing our load. That could be some, it could be some utility like a fire or something, but we've represented it with a resistor. So they go through this load, they go back through, they go over here, they're back. Now they're back here at this set of 4 diodes again. So where's it going to go? Well, it can't go through this way. Potential here is higher, so the charges want to be flowing to a lower potential, so they can't go through there. So the only way they can go is through here. So finally they go through here and they're back then and completed the circuit. So they've gone from plus to minus and they've completed the circuit. Let me just go through that one more time. They've gone through here, didn't go through there, gone through here, couldn't go through there, so they've gone all the way through there, down through there, back to here, can't go through this way because of the high potential, so they've had to go through there, back to minus. So that's the case when the charges are actually flowing in this direction. So what happens when they're 1/50th of a second later when they're moving in the other direction? So now let's think of the charges going up. So the induction has caused these charges 1/50th of a second later now to go in the opposite direction. So then we can think of that top bit as being the plus, and this now is the minus. So now we've got the situation where charges are coming out of here, they get to this point here. So where they're going to go? Well, they can't go through there because there's a bar. So they have to go through this diode. Again, they can't go down here because there's a bar. So again, they go in the same direction as what the other polarity was. They're going through here. They go through this load, through there, back to here. Now where are they going to go? Well, they're not going to go in this direction again because you've got the plus side on here. So it's a higher potential. So they can't go through there. So they've got to go through this diode. They're not going to go through this one because remember, this is also a higher potential because we're going through this way now. So the only way they can go is back down here, through here, and we're back at the minus. So again, we've completed a complete circuit here. We've gone back, we've gone from here down to here. Just go through that quickly again. So we go to here, we can't go down there, we go through here, and we're round here, down here, up to here. Again, we can't go through here because that's a higher potential. We have to go through this one. Finally, we can't go through that one again because it's a higher potential on this side. So we go down here, through there, and we've completed the circuit. So remember, whenever you want charges to flow, you must have a completed circuit. And what's interesting here, we've just shown you that the charges are going to go through that load always in the same direction. So the charges are going to flow through that load. They're never going to flow from minus to plus. They're never going to flow from here to here. They're always going to flow in this direction. So when we get to this side of that series of 4 diodes, charge always flows in this direction. In other words, we've converted a AC signal into a DC signal. It's all positive. The signal's still there, the up and down part's still there. It's just that all the down parts now are up on the plus side. So I've showed it here. So here's the original AC signal. Yeah, that's going to be the same here. Remember, when it goes negative here, it's still coming out on this side. So that gives us another positive swing. So we're measuring the voltage across here now on this side. And you can see they're all positive. This is what rectifying does, is it takes an AC voltage and converts it to what's called a pulsating DC voltage. It's called pulsating because remember, we've still got the pattern of this signal, it's just that it's all positive now. So that's what the rectification does. So now what we're going to do is take that rectified signal there, that pulsing DC voltage, and try and make it a bit smoother. Because if you want to run like a radio or an amplifier, you don't want all this spikiness going on because it causes distortion and noise and it just won't sound very good. So what you want to do is you want to smooth that out to a nice sort of steady voltage as you can get. So we're going to talk about that next stage then. To do that is called smoothing. So let's go and have a look at that. So we've got exactly the same circuit here, and all we've done now is we've introduced this capacitor in the middle. So we've still got the load. We've got these 4 diodes. You don't normally have 4 separate diodes. They're normally inside one package called a rectifier. The only difference is this component here, this capacitor. So what does capacitor do? Remember, we've got this swinging, pulsating DC voltage here, like that. Now, what we really want is a smooth DC voltage. We want something that's kind of like a straight line, or as close as we can get to a straight line. So there's a way we can do this is if we place a capacitor in here, as shown, and you'll notice that when the voltage starts to drop, eventually it goes right down to 0. So the voltage, there's no potential difference up here between here and here. At the highest potential, this capacitor is going to charge up. When this voltage here from the secondary winding has dropped down to 0, it means that this capacitor voltage is going to be higher. So what's going to happen is the charges then are going to flow from the capacitor and through the load. So what's actually happening is the capacitor is making up the shortfall. So you end up with this. You end up with the capacitor filling in these gaps. That's exactly what happens. So if you look at the output, if you was to measure the output here now on an oscilloscope, you would see that the voltage now is no longer this pulsating DC voltage, but it's this much smoother, steady. I put in the little dotted lines there that showed the original pulsating DC voltage, but on top of that is the actual output voltage that we'll measure, and you can see it's nicely smoothed out. It's not completely smoothed out, and that's what we call a ripple voltage. So although we've got a very smooth voltage now, and that will do for a lot of utilities, a lot electrical items that you want to run, that would be fine. But for some, again, for very for preamplifiers and very intricate circuits, you want even more of a rock steady voltage. You want it to be almost like completely flatline. You want a really steady voltage, say of 9 volt, and it doesn't change off 9 volt, within about 0.1 of a volt or something. Now, to achieve that, you can't get that with this. You need something else, and that's what we're going to talk about next, and that's called the regulator. So let's go on to the regulator and talk about that. Okay, this here is the regulator circuit here. This circuit here is a simplification of this circuit. With this circuit, I've removed all the capacitors and the Zener diode. This is a protection diode, and the capacitors give you a bit more smoothing. But to understand how this regulator works, it's better just to keep it to the components that actually set the output voltage. And it's so to understand a regulator, you only need to know 3 components in it, really. If you understand how those 3 components work together, then you can understand how regulators work. So I'm just going to concentrate on those by redrawing this diagram, so we've got rid of all the capacitors and everything. So we've got the voltage regulator, which in this case is an LM317. We've got 2 resistors here. Now these 2 resistors will dictate to us what the output voltage will be, and it's because of the way the regulator acts, or the way it works inside. So I'm going to describe how this works. Now, with regulators, the important thing to understand about regulators is they provide an input voltage, and then the output voltage will be dependent on the value of these resistors. The trick with the voltage regulators is they maintain a voltage drop between the output port here and the adjust port here. A voltage here is always maintained by the internal workings of this of some voltage reference value. In the case of the LM317, that voltage reference value is 1.25 volts. What that means is no matter what happens with the output voltage, this regulator will always maintain that the voltage drop between this point and the adjust terminal is always 1.25 volts. That effectively means the voltage drop across R1 is also maintained at 1.25 volts. Yeah, that's the thing to understand with the voltage regulator, is that it always maintains a voltage drop of 1.25 between the output port and the adjust terminal. Knowing that, we can look at these 2 resistors, and we've got a load resistor on the output, and that we can measure our voltage drop across there. Now the voltage drop across this load resistor is the same voltage drop that's across the top of R1 to the bottom of R2, so that potential difference is the same as this potential difference. Because of that, we can describe this part of the circuit just using a voltage divider. First thing I'm going to do is just write down what the voltage drop is. Well, the voltage drop, VO, is simply the voltage drop across R1 plus the voltage drop across R2, which is what I've written here. Now the voltage drop across R2, because we've got this, what happens in the regulator, it maintains a small current through here. It will adjust that current to always maintain this 1.25 volts. So there needs to be a current flowing, and that current will always flow through R2, and that actually gives us the voltage drop across R2. So it's going to be this adjust current times R2. Now this current is normally really small. This value here is going to be negligible. You can just ignore that and don't even take any notice of this term at all. With a voltage divider, remember the voltage drop across here is going to be Vref, so we can say Vref is over R2 at R1. That's the fraction of the voltage that's dropped across R1. It's the fraction across R1 against the whole of the resistance down here. And if you know voltage dividers, you know what I mean. So R1 over R2 at R1 times this VO. So that's the voltage out. That gives you the standard voltage divider formula here. Now, of course, you can just rearrange this, because what we want at the end of the day is VO. We want to be able to set values for VO. So we'll rearrange this, and all we do is just multiply through by R2 and R1 and divide through R1, and we get this. So we've got it in terms of the voltage out now. So the voltage out is basically R2 add R1 over R1 times the Vref. And if you know simple algebra here, you can rearrange that to be 1 add R2 over R1. So basically we've got the voltage output is a function of R2 and R1, because remember Vref is always going to be 1.25, and we're going to ignore that last term because it's so small. We'll just ignore it. So what does that mean? Well, it means that if we want to set a voltage out here, we can set it to basically any value we want just by selecting the appropriate value of R2 and R1. So just to give you an example of that, let's go here to some of these examples. I've just repeated here at the top. The adjust current here is about 50 microamps, so it's negligible. So hence we can write V0 equals 1, which I've just repeated down here. Now, the regulator, as I said before, it locks down the voltage drop across R1 to Vref equals 1.25 volts, no matter what the output voltage tries to do. So that's the point here. So no matter what's going on, that voltage drop across these two terminals is always going to be 1.25 volts. So just basically repeating what I've said before. Now given that, we can use this formula then. So let's just try an example. Let's pick two random values. Let's say R1 equals 10k and R2 equals 100k. That comes out as 1.25 times 1 add 100 over 10, which is 11. So 1.25 times 11 gives us 13.75 volts. Now if we just change R2, just pick R2 here and just change R2 to say 10k, stick that into our formula. 10 over 10 is 1, 1 add 1 is 2, 1.25 times 2 is 2.5 volts. So you can see, no matter what we do, all we have to do to get the voltage output that we want is to adjust either R2 and R1. And if I show you the actual one that I've built here that I use for the guitar amp, you'll see what I mean. So here's the one I use for the guitar amp. Now this potentiometer here, which you can see is there, and by the way, there's the rectifier, and this here's the potentiometer, and that potentiometer is basically R2, so it's this value here. So I'm actually going to be able to set different voltages by turning that, and that's what we've got here. We've got a variable linear voltage power supply, and inside the larger box there is the transformer. So the transformer goes in there. It's earthed, of course. Make sure if you're ever using a metal box that you earth out the earth wire coming from your mains. Make sure you use earth mains and that you connect the earth wire to the side of the tin. Normally you can just connect that earth wire to the bottom bracket of the transformer, which is bolted to the tin. Then the reason you do that is if for any reason one of the live wires, you know, the neutral or the live brown wire was to come disconnected and hit this side, it would earth immediately out to ground, and so if you touched it, it wouldn't hurt you, it would just go straight to ground. So that's a safety feature. Make sure you always use an earth when you're dealing with 240 volts. You want to make sure you always use an earth on your lead. If you had a plastic container, you probably wouldn't need it, because obviously a plastic is an insulator, but this is metal, so, or tin in this case, so you do need it earthed out. But if you earth it out, you're perfectly safe. As long as you make sure you do all the connections securely, you should be fine. So that's the whole thing. That's how you can build one of those by just using this. So remember what we did there. So we've just gone through the whole thing. We basically use this circuit here. We've done the transformer. From the transformer, you go through the diodes. You get a pulsed DC voltage, and then you smooth out that pulsed DC voltage, and then finally you go through the regulator, which fixes it at about whatever voltage you want. Remember that the important thing when it comes out of the regulator, not wavering. If you set it to 9 volts, it'll stay on 9 volts, you know, within a few millivolts, and that's the point of the regulator. It gives you a very fixed voltage within, you know, quite very, very small margins. It'll give you a very solid fixed voltage. So that's the whole thing. That's how it works. If you want to build one of these, you can just use that circuit. I mean, there's the circuits in here. That's everything in there. There's the smoothing caps, the 4 diodes in there. Got your output power here, so you stick in your application, whatever it is, and then your transformers at the bottom, like I say, with the input port here. So that's it. That's the whole thing. And that circuit is exactly what's in that tin that I've just shown you. It's just those components, only a few components, and it's very easy to build. So I hope this has been helpful to you.